Lesson 1.2, Task 3. Identify key characteristics in context. Identifying key features of a graph in a real-world context gives you tools to interpret the function's behavior in its context and may help you identify and interpret trends. A car's suspension system connects the body of a car to its wheels. Springs are one component of the suspension system. The graph shows the vertical displacement of the spring in a car's suspension after the car hits a bump during a suspension test. Identify and interpret the key characteristics of the graph. All right, so if we look at the graph here, we can see that it says the vertical displacement of suspension, and on the x-axis we've got time in seconds, and on the y-axis we've got vertical displacement in meters. So you can see at time 0 it's about 0.09, and then it drops below 0 and then goes back up and goes back down and back up, and it kind of levels out here. So this is the displacement during when it hits the bump. And you can see after it gets past the bump, not even about a second after it hits the bump, then it's kind of back to normal. There's no displacement. All right, so let's see what it says. Observations and interpretations. The greatest change in the spring's position occurred within the first 0.2 seconds of hitting the bump. So you can see the first 2 seconds of hitting the bump, this is 0.2. So you can see here, that's the biggest change. The graph shows a maximum value at 0 and at 0.45. So at 0, here's a maximum value here. That's the highest point on the graph. And then you can see it goes back up here about 0.45 is another maximum value. All right, so it says, how can the displacement value at 0 be a maximum value when it is not located at a turning point? All right, so our choices are the value at 0 is a maximum because it is greater than the other displacement values for all other values of time. The value of 0 is a maximum because it is less than the other displacements. Well, you know that a maximum is greater than, not less than, other displacements. So it'd have to be the first one. All right, so it says the lowest displacement, about negative 0.035 meters, occurs at about 0.2 seconds. The graph also shows a minimum value at 0.65. So 0.2 is here, so that's going to be our lowest point, and it shows another low point about 0.65, so right in there. Okay, so it says what makes the displacement value at 0.65 seconds a minimum value when the displacement at 0.2 was less. Okay, so it says there is a turning point where the graph changes from increasing to decreasing. There is a turning point where the graph changes from decreasing to increasing. So at 0.65 you can see it's going down and then back up, so it would be decreasing to increasing. So from decreasing to increasing. All right, so it says the graph is increasing from 0.2 to 0.45 and 0.65 to 0.9. The graph is decreasing from 0 to 0.2 and from 0.45 to 0.65 and from 0.9 to 1.2. All right, so when it says the graph is increasing, okay, it just means it's going up, okay? So if you look here from 0.2 to whatever that other point was, it's going uphill. And when it says it's decreasing, it means it's going down, okay? So you always read a graph from left to right. If it's going up, it's increasing. If it's going down, it's decreasing. So it'd be decreasing, increasing, decreasing, increasing, okay? So those points were just values on the x-axis or time in seconds. All right, how can 0.45 seconds be part of both an increasing and decreasing interval? All right, so that's the turning point that we talked about a minute ago. And so since it's the turning point, it kind of is right in the middle of increasing or decreasing. All right, so it says the average rate of change from the first maximum to the first minimum is about negative 0.675 or negative 0.675 meters per second. All right, so it says, does this rate of change accurately represent the entire graph? All right, so they're looking at the first 0.2 seconds. So if you go back and look at the first 0.2 seconds, does the average rate of change of this portion of the graph here represent the average rate of change of the whole graph? Well, no, not exactly, because that's when it first hits the bump, and that entire portion is decreasing, so the average rate of change is going to be different than it would be if you're looking at the whole graph. So let's see what our choices say. Does the rate of change accurately represent the entire graph? Explain. So we know it's going to be no, but which one of these is the best answer? So no, the graph has increasing intervals, so a better representation of the entire graph should be a rate of change on the increasing interval. Well, there's no increasing intervals on that interval. So it says no, the graph has intervals of decreasing and increasing, so the average rate of change of only a decreasing is not representative of a graph of the whole thing. Okay, so that is true. So the whole graph has both increasing and decreasing, but the portion that they asked us to look at was only decreasing, so that does not represent the entire graph. All right, that is all for task 3. If you have any questions, please let me know. Lesson 1.2, task 4. Apply function characteristics to a real-world context. A description of a real-world situation can be used to create a graph. Always pay careful attention when choosing the axis for a graph, since these determine what the values in the graph represent. All right, so if you look at the graph here, it looks like a roller coaster, and it's showing that there's a maximum elevation at 205 feet. So it says a roller coaster ride begins at ground level. The first 40 seconds of the ride includes only turns with no changes in elevation. Next, the roller coaster rises steady for 50 seconds to a maximum elevation of 205 feet, then plunges back to the ground level in only 8 seconds. The next 6 seconds, it rises to an elevation of 100 feet, then drops back to ground level in 6 seconds that follow. The remaining 90 seconds of the ride include small inclines and drops before returning to the starting point. All right, so it says sketch the graph. All right, so if you sketch the graph, you're going to have time in seconds. It says the first few seconds, it just went through turns. It didn't really change elevation, and then it went up so many feet, and then plunged back down, and then back up and back down, and so on and so forth. All right, so sketch the graph. Doesn't have to be perfect. It's just a sketch. But if we look at what they have sketched here, you can see the first 40 seconds, the elevation did not change. And then it went to a high point, dropped in 6 seconds, went to another peak, dropped, and then did a few things and then finished. Okay? All right, so it says match the unit and scale to the axis. All right, so you can see here, time in seconds would be our x-axis, and elevation would be the y-axis. All right, how does this description of the scenario allow you to identify important values of the graph? Okay, so it allows you to see the maximums and the minimums and the constant rates and that sort of thing. All right, so it says y is the part of the graph from 0 to 40 horizontal. Okay, so remember it did some turns, but it did no elevation change. So the graph is horizontal because the roller coaster is not moving, is at a constant speed, or is at the same elevation. So the roller coaster is at the same elevation the whole time. All right, what are the average rates of change for the 2 greatest drops? Okay, so the average rate of change for this drop is going to be probably the largest rate of change. And then for this drop would be the second largest rate of change. So the average rate of change for the first drop is about I would say negative 25.6 because that was the biggest drop, so that would be feet per second. And the average rate of change for the second drop would be, all right, so we know it's going to be negative because it's dropping. So when the roller coaster is dropping, it has to be negative. And we know that the second drop was a little bit smaller than the first drop. All right, how do the average rate of change of the two greatest drops compare? Well, the first rate of change, negative 25.6 feet per second, and the other one is negative 16.7 feet per second. This average rate of change is almost, 1.5 times greater than the second one. Okay. All right, so that is all for task 4. If you have any questions, please let me know.